Good morning, everyone. I am Dipanshi from Basic Chemistry Honors Second Year. Today, I am here to represent the topic power cycles and Carnot engine. Power cycle. Most power producing devices operate on cycles. To make simple thermodynamics analysis possible, we use the concept of ideal cycle. These idealized cycles serve as starting point for more in-depth studies. Heat engines are designed to convert thermal energy to work. Thermal efficiency, eta, defined as benefit by cost, W net by Q, or eta is equal to W net by Q in. Ideal cycles are internally reversible, but unlike the Carnot cycle, they are not necessarily externally reversible. Thus, the thermal efficiency of an ideal cycle in general is less than that of a totally reversible cycle operating between the same temperature limits. Carnot cycle. Therefore, nobody can develop a cycle more efficient than the Carnot cycle. Hence, the conclusion is Carnot cycle is more efficient than anyone else. Common assumptions in idealized power cycles. The cycles do not have any friction. Thus, no pressure drops in working fluid. Due to the absence of friction, कोई भी pressure ड्रॉप वर्किंग फ्लूइड में काम नहीं करता. All expansions and compressions are considered quasi-equilibrium. No heat losses in pipes and other components. Change in kinetic and potential energy are negligible, except for nozzles and diffusers, which are specifically designed to change the velocity of passing fluid. PV diagrams and TS are useful as visual aids in analysis of ideal power cycle. Areas enclosed by the process curves in T and PV diagram represent the network of idealized cycle. Remember that an ideal power cycle does not involve any internal irreversibilities, thus one can conclude. On a TS diagram, a heat addition proceeds in the direction of increasing entropy and vice versa. The area under the process curve on a TS diagram represent the heat transfer for that process. The area enclosed by the process curve on both TS and PV diagram represent the network of the cycle. The ratio of the area enclosed by the cyclic curve to the area under the heat addition process curve represent the thermal efficiency of the cycle. On a TS diagram, a vertical line represents an isentropic process, no heat transfer and reversible. Now we will discuss about the Carnot cycle. Carnot cycle is the most efficiency power cycle as I have told it before, and it is composed of four totally reversible processes. So process 1 to 2, isothermal heat transfer, heat supply, heat is applied at constant temperature. Process 2 3 is entropic expansion, air expand as entropically from the high pressure and temperature to the low pressure and temperature. Process 3 4 isothermal heat transfer, condenser or heat rejection, heat is the rejected at constant temperature T1. Process 4 to 1 isentropic compression, the air compresses isentropically to the high pressure and temperature. Thermal efficiency of the Carnot cycle can be calculated from eta is equal to 1 minus TL by TH. Now, Carnot cycle is not limited to the processes of a closed system taking place in a pistons in cylindric assembly. Figure 2-3 shows the schematic and accompanying PV diagram of a Carnot cycle executed by water steadily circulating through a simple vapor power plant. 1 2 to the steam exciting the boiler expands adiabatically through the turbine and work is developed. The steam temperature decreases from TH to TL. Two-phase mixture flows through boiler where heat rejection occurs at constant temperature TL. The mixture liquid vapor enters the pump or compressor and its pressure increases. This is an adiabatic process and requires input work. The saturated liquid at high temperature enters the boiler where a change of phase from liquid to vapor occur at constant temperature. Isothermal heat transfer. Carnot cycle are not encountered in reality since achieving isothermal heat transfer is very difficult, needs very large heat exchangers and long time. Also process 3-4 require a pump or compressor then that can handle two-phase mixture, which is impractical. The real value of the Carnot cycle comes from its being standard against which the actual or ideal cycles can be compared. Reversible heat engine efficiency is maximum, determined by the working of heat engine in four successive steps. As I have told, work done by heat absorbed is equal to eta. Cylinder, we have taken a cylinder which have weightless frictionless piston filled with ideal gas. N is equal to 1 mole. All walls should be insulated except at the bottom. Now we have three conditions on the heat source, on the heat sink: insulating, non-conducting material. In both the cases of first two, source and sink, heat capacity is infinite. For the completion of steps of Carnot cycle, T2 must be greater than T1. Can be shown heat by PV graph. Isothermal expansion from A to B, adiabatic expansion from B to C, and isothermal compression from C to D and from D to A, adiabatic compression. Now, first step, place the cylinder in heat source for isothermal expansion. Work done is equal to W1 Q2 nRT ln V2 by V1. Place cylinder on insulating non-conducting material for adiabatic expansion. Work done W2 is equal to CV T1 minus T2 is equal to minus CV T2 minus T1. Place the cylinder on heat sinks for isothermal compression. Plus W3 is equal to minus Q1 is equal to nRT1 ln V4 by V3. Now fourth step, place cylinder on insulating non-conducting material for adiabatic compression. W4 is equal to CVT2 minus T1. Now net work done, W is equal to nRT2 ln V2 by V1 minus CV T2 minus T1 plus nRT1 ln 4 by V3 is equal to plus CVT2 minus T1. At last, W is equal to nRT2 ln V2 by V1 plus nRT1 ln V1 by V2. We know that TV gamma minus 1 is equal to constant. T is equal to constant V gamma minus 1. T1 by T2 is equal to V2 gamma minus 1 by V1 gamma minus 1. T1 by T2 is equal to V1 gamma minus 1 by V4 gamma minus 1. And T1 by T2 is equal to V2 gamma minus 1 and T2 by V3 gamma minus 1. V1 gamma minus 1 divided by V4 gamma minus 1 is equal to V2 by V3 gamma minus 1. Now V1 gamma minus 1 by V2 gamma minus 1 is equal to V4 gamma minus 1 divided by V3 gamma minus 1. V4 by V3 is equal to V2 by V1. W is equal to NR ln V2 by V1 T2 minus T1. NR ln V2 by V1 T2 minus T1 is equal to T2 minus T1 by T2 divided by nRT2 ln V2 by V1. W by Q2. Eta is equal to Q2 minus Q1. Eta is less than 1. Efficiency always less than unity. A heat engine absorbs certain amount of heat from source, converts a part of it into work and returns the rest to sink. Impossible to convert heat completely into work. Now we are discussing some questions related to Carnot cycle. What is a working fluid in Carnot cycle? So our answer is the working fluid in a Carnot cycle is an ideal gas. What is a Carnot heat engine? Carnot engine is a theoretical engine that operates on a reversible Carnot cycle. It has maximum efficiency that a heat engine can possess. Name the process involved in the Carnot cycle. It involves four processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. What happens in the isothermal expansion process? In the isothermal expansion process, gas is taken from P1 V1 T1 to P2 V2 T2. Heat Q1 is absorbed from the reservoir at temperature T1. The total change in internal energy is zero, and the heat absorbed by the gas is equal to work done. Is Carnot cycle reversible? The Carnot heat engine cycle described as a totally reversible cycle. What is a working fluid in Carnot cycle? The working fluid in a Carnot cycle is an ideal gas. What is a Carnot heat engine? Carnot heat engine is a theoretical engine that operates on a reversible Carnot cycle. It has maximum efficiency that a heat engine can possess. Name the process involved in Carnot cycle. You know that there are how to calculate Carnot cycle efficiency. The efficiency of a heat engine is defined as the ratio of the heat converted into work in a cycle of the total heat supplied to the source. Eta is equal to work done by heat supplied. Q1 minus Q2 divided by Q1 is equal to 1 minus Q2 by Q1. If T1 and T2 are the temperatures of the source and the sink, then Q2 by Q1 is equal to T2 by T1. Therefore, eta is equal to 1 minus T2 by T1. Why is Carnot cycle not practically possible? The real engines are not reversible due to the reasons like heat transfer, friction, etc. Whereas the Carnot engine is reversible. In the Carnot cycle, the reverse process takes place very slowly, but real engines work fast. The temperature of the source and sink is kept constant in the Carnot cycle, but in a real engine, heat transfer will occur only if there is a difference in temperature between the source and the sink. When will the efficiency of Carnot cycle will be maximum? The efficiency of Carnot cycle is maximum when eta is equal to 1 minus T2 by T1. T1 and T2 are the temperatures of source and the sink respectively. Now we will discuss why is Carnot cycle important. Carnot cycle is a theoretical thermodynamic cycle that represents the most efficient heat engine possible. In thermodynamics, the Carnot cycle is important because it represents the maximum efficiency that any heat engine can achieve. It is a theoretical cycle that consists of four reversible processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. The cycle is named after French physicist Sadi Carnot, who first proposed it in 1824. Now, why Carnot cycle is significant? Now, Carnot cycle is also important because it provides a theoretical framework for understanding the behavior of a real world heat engine. While no real engine can achieve the maximum efficiency of the Carnot cycle, engineers can use the Carnot cycle as a benchmark for evaluating the performance of real engines and identifying ways to improve their efficiency. In summary, the Carnot cycle is a fundamental concept in thermodynamics that establishes a theoretical limit on the efficiency of heat engines. It is also important for understanding the behavior of real world engines and for identifying ways. Carnot cycle is significant because it establishes the fundamental limit on the efficiency of a heat engine. The efficiency of a heat engine is defined as the ratio of the work output to the heat input. The Carnot cycle shows that the maximum efficiency of a heat engine is determined by the temperature difference between the hot and cold reservoirs. The higher the temperature difference, higher the efficiency. Thank you.